Hey everybody, in this next video lesson, I'm going to show you how you can calculate the amount of electrical energy that is produced when you put two half cells together in order to make a voltaic cell. In order to understand what's happening, we need to once again think of the voltaic cell in two half reactions. Now, cell potential, which is measured in volts, is basically taking the two half cells and subtracting the electrical potential at the cathode from the electrical potential at the anode. These electrical potentials are identified in extensive tables that you will find that I will show you coming up on the next slide. But all of them are always listed as a reduction potential. Now I understand that in a voltaic cell, half of the reaction is doing a reduction, but the other half is doing an oxidation. But these tables will only show what's happening in each half cell as a reduction potential, which is why we always take the reduction at the cathode and subtract the reduction at the anode. Now each one of these metals, when they reduce, offers up a slightly different voltage, some of which are even negative. But for example, silver reducing from a +1 charge to neutral results in a voltage of plus 0.8, whereas something like copper +2, I should say copper 2+, getting 2 electrons and resulting in neutral copper has a voltage of positive 0.34. But then there's metals like aluminum, for example, when it reduces by gaining 3 electrons to become neutral aluminum, has a voltage of negative 1.66. Now these numbers can be used to calculate the cell potential. The formula for calculating cell potential is take the electrical potential at the cathode, which is the more positive number, and subtract it from the electrical potential at the anode, which is the less positive number. Because when you subtract these two numbers, the resulting cell potential, that is the overall electrical output of that cell, should always be a positive number. So if you subtract two half cell potentials and get a negative number, well, you actually have the electrodes mixed up, and you simply just need to switch their position, because what you're actually doing is subtracting the anode from the cathode, but we always want to subtract the cathode from the anode. It's also worth noting that these electrical potentials are all happening at standard state conditions, that is 1 atmosphere of pressure, 298 Kelvin, but also, as I touched on in a previous video lesson in a previous chapter, that now we're talking about standard molarities for aqueous solutions, because these redox reactions happen in aqueous solutions most of the time, so that we're talking about a concentration of 1.0 molar. Here's a table of electrical potentials, reduction potentials, for all these different situations, all of which are, as I mentioned, reductions. It's worth noting once again that these are standard reduction potentials. But you can see that the E, or the voltage, is organized from more positive to less positive. Now let's take a look at the top of the list. We've got things like oxygen reducing or bromine reducing, or even nitrate reducing, the nitrogen as part of nitrate reducing. And so all these are non-metals, and they have a very positive voltage. These are most likely to be the cathodes in an electrical cell. But honestly, these are unlikely to be the case, because oftentimes, at least the ones that we're working with in class, the metals are what we're going to be using for the cathode and the anode. And so your first metal you see on this list is silver, and it's got a positive 0.80. The more positive it is, the more likely it is to be the cathode in a voltaic cell. But as you go down the list, once you get into the negative numbers, these are metals that are more likely to be the anode, because as we remember, oxidation happens at the anode, and if you have a negative reduction potential, that means you have a positive oxidation potential. Now we don't really talk about oxidation potentials because that's just kind of confusing, but remember, an oxidation is the opposite of a reduction, so an oxidation potential is a flipped sign of the reduction potential. So these substances with negative voltages are more likely to represent metals that would be used as an anode in a voltaic cell. And notice the one at the very bottom, the one with the most negative or the most likely to be oxidized because it's got the smallest reduction potential, is lithium, which is one of the ions used most often in lithium-ion batteries or lithium-ion voltaic cells. You will always be given a list of reduction potentials that you might need to use in order to do a problem on a quiz or a test. Or in a particular question on the AP test, they might give you like a smaller list of reduction potentials and ask you to use one or two of them in order to answer the problem. So you do not have to memorize this, even though it's found in your textbook. And this by no means represents all of the metals or all the substances that can be reduced. These are just happen to be the most common ones that you'll find. But there are many, 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 many more examples of different substances that can be used in voltaic cells besides the ones that you see on this list. Now we're going to talk about the different things that you can do when you're given some reduction potentials and some reduction reactions, things that you could be asked on upcoming quizzes or tests or even AP tests. The first thing you see is that you have two reactions, both of which represent reductions. And so maybe the first question you might be asked if you see this information is, what does the overall reaction look like? Well, you can't have two reductions, so you have to have a reduction and an oxidation. What that means is one of these reactions has to get inverted or turned around before you can add it together. Because as you remember from just a few days ago when we did some balancing of redox reactions, you have to represent the half cells, one in an oxidation and one in a reduction. Now the reduction is going to stay as it's written because these are reduction potentials, these are reduction half reactions, and so one of these is going to stay and the other one is going to get inverted. Now remember, the one with the highest electrical potential is what's happening at the cathode, and reduction happens at the cathode. So the one that has the highest cell potential is the reduction. That means that the other one, the smaller of the two, is the oxidation. So the smaller one needs to get flipped around and inverted in order to be added together. So when you do that, what you have is Cu gives you Cu2 plus 2E minus. Now we need to multiply by the lowest common multiple of the electrons. Now the first half reaction only has one electron, where the second half reaction has two electrons. So let's multiply this top half reaction by 2. Everything gets multiplied by 2. Now what's interesting about cell potential is that even though the stoichiometry of this top reaction changed, it does not affect the reduction potential of that half reaction. Stoichiometry does not affect the reduction potential. If this was an enthalpy, then it would be affected. Or if this was, say, used to calculate an equilibrium constant, then the stoichiometry definitely matters. But for calculating cell potential using reduction potentials, changing the stoichiometry does not change the reduction potential of a half reaction. So we've got these two half reactions, and now we can see that 2 electrons are lost, 2 electrons are gained, so let's bring the two reactions together. And what you have is 2 irons 3 plus copper gives you 2 iron 2 plus copper 2 plus. And so we now have a balanced reaction. Another question you might be asked is, calculate the cell potential. Well, all you need to do is go back up to these two numbers again and take the bigger one and subtract the smaller one. The one that's bigger is at the cathode, the one that's smaller is at the anode. Subtract the two reduction potentials, bigger minus smaller, and you get the overall cell potential. Well, the overall cell potential, take 0.77 minus 0.34, you get 0.43 volts. So that's the cell potential. Once again, that's standard conditions. And the last thing that you might be asked is to identify which reaction is happening at the cathode and which is happening at the anode. But we already mentioned this now a couple times. The bigger number is what's happening at the cathode because that's the reduction, and the smaller number is what's happening at the anode because that's the oxidation. And so you might be asked to identify the reaction happening at the cathode or the anode or both, and you simply just use the size or magnitude of the cell potential values in order to determine that. I do want to mention that if you are asked to identify the reaction that happens at the anode, you need to make sure that the reaction is in the form of an oxidation. What I mean by that is that if I ask that question, or you see that on a test, and you write Cu2 plus 2E minus gives you Cu, then I will actually mark it wrong, and so would a reader on the AP test, because this is a reduction, not an oxidation. If it's happening at the anode, it has to look like an oxidation, so you have to show electrons being lost. So let's finish this off with one more practice problem. And of course, as you know me, I show you how to do one, and then we try one. So let's take a look. Calculate the cell potential of the galvanic cell, or what is referred to as a voltaic cell, with silver and zinc. And I've got the reduction potentials of silver and the reduction potentials of zinc. So the first question is, calculate the E cell. So I take the larger one minus the smaller one, and I take 80 minus a negative 0.76. When you subtract a negative, it becomes more positive. So the answer is 1.56 volts. Next, I want to balance the reaction. Remember, one of these is going to stay as it's written, and the other one is going to flip around or invert. And remember, the smaller of the two electrical potentials is the anode, and the anode is the oxidation, and so you need to flip the smaller one around. So we flip it around so that the zinc equals zinc 2 plus 2 electrons. We multiply the top reaction by 2 to get 2 silver ions plus 2 electrons gives us 2 silver atoms, and then we combine the two half reactions back together again, and the resulting reaction is 2 silver ions plus zinc gives me 2 silvers plus 1 zinc plus 2 ion. Next, we're going to identify the cathode and the anode. The cathode is, of course, the one that's happening where the reduction is, and that would be the larger of the two numbers. And the anode is the smaller of the two numbers. So that's easy. It doesn't say write the reaction necessarily, it just says identify. So you just need to point to one of the two half reactions, that's the cathode, and one that's the anode. We're going to sketch out a picture of the voltaic cell, and we are going to make sure to identify the electrodes and show the direction of electron flow. And so what we're going to do is have two little beakers here on the bottom, and on one side I'm going to put a silver electrode, and on the other side I'm going to put a zinc electrode. And so these are my little chunks of metal, and I'm going to connect them by a wire over the top. And then I can't forget that there's a salt bridge. With no salt bridge, the reaction doesn't happen. So we sketch in a little salt bridge here. Now I've got to figure out, okay, oxidation happens at the anode, and the electrons flow away from the anode. So I've identified the zinc as the anode, and so with that being said, I know that this one over here is the anode, and the electrons are going to go up the wire, across, and back down towards the cathode. So that's what I mean by show the directional flow of the electrons. Well, that takes care of this video lesson. Thanks for watching.